Welcome, everyone. I'm very happy to introduce you Jane Arthur. Jane Arthur from our institute. She studied mathematics. She got a degree in mathematics in Leeds University. And then she got a PhD in applied mathematics in Leeds. She doesn't want me to tell you which year this was. But she came to Mexico as a postdoc at Instituto de Astronomía in Mexico City around the 90s, early 90s. And then she became a researcher, or then she came here when our institute didn't exist, and it was Unidad Asociada al Instituto de Astronomía. And then she became a researcher for UNAM in 1994. Already here in Morelia?
No. Aquí in 96. Here in 96.
96, okay. So you started in Mexico City. Okay.
4 years.
She's interested in theoretical astrophysics, hydrodynamics, stellar evolution. She's very good at writing code, radiation analytical codes, and it's always a pleasure to work with her. So, and she's also has other interests. She's recently got a master's degree in sustentabilidad or related degrees, and this is her own public announcement. She will be talking about runaway Wolf-Rayet stars in our galaxies. So, please welcome her so she feels our warmth.
And so before I start the talk, I'm going to make a public service announcement on behalf of the Comisión Local de Sustentabilidad. For about 5 years now, we've had these islands of separating rubbish. We've, from time to time, we look in the bins, and it's very interesting, the random things we find in there. So just to draw your attention that all of these bins have instructions associated with them, and it will be nice if people follow them. So eco-enlace, these are the big cardboard boxes. They take paper, mainly paper that you don't use to come out the printer. If they will take cardboard, but these fill up very quickly, so undo your cardboard boxes and put them behind the eco-enlace box. Do not put anything that's been anywhere near food in the eco-enlace box, like pizza boxes do not go anywhere near that. So we then have these 4 plastic bins. This one, the green one, is for organic stuff, which can take food, fruit, peels, stones, whatever. But don't put anything that's meat-based in here, and don't put any food wrappings in here either. Yeah. So at some point in the hopefully not too distant future, this will be composted on the campus. So anything that's got any wrappings there, we just complicate that process. These, the yellow and the blue bin are for recyclable materials, plastics that are 1 or 2. So that's in the little triangle on the plastics. 1 is PET and 2 is the sort of soft ones. These can be recycled, but they need to be clean. So if you got like a yogurt pot, you need to rinse it out before it goes in there. If it goes in the bin with food on it, then it contaminates the whole bin. It can't be recycled. Same with the sort of glasses and tins. They need to be rinsed before they go in the bin. Anything that's dirty that you can't be bothered to rinse out, or that you don't know whether it goes in any of these others, just put it in others. So anything that's contaminated with food, or you don't know where it should go, put it in others. Yes.
Question.
Batteries do not go in any of these.
Well, what people that collect the garbage, they put everything together, and then they separate it.
No, they put bags within bags, and as long at the caseta, they do now have big containers for separating stuff. They have one that's supposedly for otros, and one for reciclables.
So this is useful, really.
It will be once they get their protocols sorted out. But the idea is that we are ready for them. We've been ready for 5 years. And they're finally getting their act together. You may notice that some of the recyclables disappear because the personnel, the base, recycle the stuff before it ever gets anywhere near the recollectores. Okay, so public service announcement. This is here we go. So this is the first talk I've given for quite a long time. I think the last talk I gave was like a week before the pandemic started in Guanajuato, and surprisingly, it was on the same sort of topic. But I've actually finished the work now, and I know what I'm talking about. So this is the result of about 5 years work, where I've learned a lot about stellar dynamics, which is something that I didn't know much about before. So the inspiration for this work is this object here. This is the ejector nebula M167 around the archetypal Wolf-Rayet star, Wolf-Rayet 124. I put archetypal in inverted commas because if anyone is giving a talk and they mention Wolf-Rayet stars, they usually put a picture of this object there. But as we're going to find out, and as some of you already know, this is not an archetypal Wolf-Rayet star. It's a very strange star. Its spectral type is WN8H, which I'm going to go into a bit later. The luminosity of this object is almost 1 million solar luminosities. It's a very bright star. Its distance, according to Gaia, is 5.5 kiloparsecs, and this puts it at Z height of about 330 parsecs above the galactic plane. And thanks to Gaia, we also have proper motions, and there are also radial velocities for this star, although, again, we're going to look into that a bit later. So its radial velocity is 190 kilometers a second, which is one of the highest measured stellar radial velocities. So this object, many of you will recognize because it was an object that Paulina Jimenez studied for her PhD. She was interested in finding out how much dust was contained in this ejector. So in order to prepare you for the results section later on, I'm going to introduce this sort of diagram now. This is the schematic of our best guess of the spiral structure of our galaxy. So I've turned it upside down because all my diagrams are this way up. So the sun is up here. This is the galactic center, and these are on the same scale. These spiral lines here are indicated by these colored bands here. And the spiral structure was was determined by Reed and collaborators in 2019 using massive observations of very young star forming regions. And according to the Reed model of the spiral structure of the galaxy, the sun is at 8.15 kiloparsecs from the center, and the circular velocity at the position of the sun is 236 kilometers a second. So this is a bit different to maybe what you've used, but it is becoming a sort of standard value now. So in this view of the galaxy from above, the projected position of this star, Wolf-Rayet 124, is here in the Sagittarius arm. So the sun's here, the galactic center is there, this star is here, and the galaxy star. So we can also find its position above and below the galactic plane. The Gaia view of the galactic structure, seen from the side, would be something like this. This is an artist's impression, clearly, but it's based on Gaia data, and we know that our galaxy has a flare. It gets wider from the center outwards, and it also has a warp. So the different components of the galaxy have different scale heights. For example, the star-forming regions that Reed et al. Used for the determining the spiral structure, they have a scale height of about 20 parsecs, whereas H2 regions associated with sort of hot young stars have a scale height of about 50 parsecs. So Other sorts of results I'm going to show you are based on diagrams like this. So instead of heliocentric coordinates, we're now in galactic RZ coordinates, and we've also introduced this angle phi, which is similar but not exactly equal to pi minus the galactic longitude. So in this set of coordinates, the galactic center is R is 0, Z is 0, and our star would be up here, at this sort of galactocentric distance of 330 parsecs above the planet. The shaded region is the scale height of all B stars as determined by Lee et al. 2019 from Gaia data. And so they fixed their OB stars using a model that includes flare and warp. So the flare is what produces this widening of the scale height as we go away from the galactic center. And the warp is what changes the position of the galactic midplane. The warp only kicks in after a certain galactocentric radius. So all the fit parameters are the things with the subscripts basically, and these numbers all plug into these equations. And if you've got a star and you know its galactocentric radius and this phi value, you can work out what should be the warp and the flare at its position. So for this position where this Wolf-Rayet star is, we can see that it's way higher than the scale height for all these stars. So given that we know its current position, we can use stellar dynamics programs to find out where it was in the past. So I'm also going to be showing trajectories of stars going backwards in time. So if the current position is indicated by a red star here, 5 million years ago, the position of the star would have been here where there's a black cross, and then 10 million years ago, open circle. And then this is joined by a line. In this case, the line color is magenta, which indicates that it's above 60 kilometers a second peculiar velocity. So in the galactic plane, projected thing, it looks like it follows a circular trajectory. But if we go out of the plane, the side view, we can see that if this Wolf-Rayet star is here now, even 10 million years ago, it wasn't within a scale height of OB stars of the galactic plane. And the dotted lines here, the brown dotted lines represent the 20 parsec scale height of the young star forming regions, and the pink dashed line is the H2 region scale, just to give you an idea how all these things compare. So even 10 million years ago, this star was nowhere near where the rest of the OB stars are. And that's important because it's thought that Wolf-Rayet stars are the descendants of massive O stars, like O stars with masses above, that originally had masses above 20 solar masses. And these stars don't live very long. So that was the sort of the introduction, preface. And so the rest of the talk, we're going to first look at Wolf-Rayet stars. What are they, and what's their role in stellar evolution? We're going to look at definitions of what makes a runaway star. How I used Gaia data to examine the stellar dynamics of lots of Wolf-Rayet stars. The problem with radio velocities. And we're going to look at some results in statistical terms, in terms of trajectories, and finally look at what makes these stars run away in the first place. So Wolf-Rayet stars, it's a spectroscopic class characterized by high photospheric temperatures and high luminosities. And their spectra indicate that these stars have modified surface abundances. The mass fraction of hydrogen is less than 40%. And so helium and other elements are more important in the spectra. And this is an optical classification. So everything indicates that these are evolved stars because they have other elements of products of fusion processes on their surfaces. They also the spectra are also characterized by broad emission lines, which indicates that they have very strong stellar winds. And then there are subtypes, because astronomers are never content with just dividing things into two. We have subtype whose spectra are dominated by nitrogen lines, and those are WN, and these are thought to be the ones that are showing the products of hydrogen burning on their surface. And then we have spectra that are dominated by carbon lines, where the suggestion is that now it's helium burning products that are coming to the surface, which are WC. And again, we have a sort of separation with the scale of the decimal scale, where light numbers or high numbers indicate light types or cooler stars, and smaller numbers indicate hotter or early types. So the combination of strong stellar winds and then products of hydrogen burning, products of helium burning, and then the cooler and hotter suggests that there's a gradual change from late type WN stars through to early type WC stars. That would be the way you would naturally think about the progression of spectrum types.
Good question, Jen. Do we know anything about the rotation? Can we say anything about the rotation from what you just said? Does it relate?
Not really. Really. Okay. Right, so I like this diagram. It's going to take me quite a while to explain it. This was published by Norbert Lange in his annual reviews back in 2012, and it summarizes what we know or what we think we know about the evolution of massive stars. So on the horizontal axis, we have sort of initial mass on the 0 and age and sequence. And the vertical axis is sort of time, but it's a fraction of total lifetime. So the star would start here, for example, and evolve through the hydrogen burning stage, and then evolve through the helium burning stage, and eventually explode as a supernova. So we see from this diagram that there is a minimum mass for stars to become Wolf-Rayet stars that's around 20 solar masses. And this depends a lot on the sort of metallicity of the original examined star. It can be higher, it might be a bit lower. So, for example, a 22 solar mass star would start as a main sequence O star, and as a hydrogen finished, it would change into a giant and supergiant, and it would become a blue or red supergiant. It would then peel off its outer layers and be visible as a WN late star, then a WN early star, this orange color, then progressively into the transition of WC, and then finally explode as a supernova with no hydrogen and no helium on its surface. So that would be a supernova 1C. Whereas higher mass stars would have a different evolution. They would not have this supergiant stage. Instead, they might have a brief luminous blue variable stage, which is when the luminosity of the star exceeds the Eddington limit. And so through radiation pressure, it has to get rid of a lot of surface mass in a short space of time. So it would eject not all its hydrogen and appear as an early type WN star, and then transition into a WC. There are some stars, very massive stars, above 60 or 70 solar masses, that can show these Wolf-Rayet characteristics even during hydrogen burning stage. So they can be classified as light type WN stars even while they're still burning hydrogen in the nucleus. And these are extremely luminous stars. They're going to lose a lot of mass at various stages of their life because they evolve. All their evolution is very close to the Eddington limit. So these arrows summarize different different evolutionary scenarios. This is for a star that's 22, 23 solar masses, this one 40 or 50, and this one for a 70 solar mass star. And the lifetimes here come from numerical simulations. The Geneva group did a lot of simulations of Wolf-Rayet stars in different scenarios. And the lower mass Wolf-Rayet stars are expected, an isolated Wolf-Rayet star will only live about 7 million years, whereas a very massive star would only live about 3 million years. So the 10 million years of life that I gave Wolf-Rayet 124 has been generous. And also it's a WN8, so where does it fit in the star? So now a few pretty pictures. This is another WN8 star. This is an ejector nebula around Wolf-Rayet 40. This is the one that disappeared quickly, is a stellar wind bubble around a WN4 star. This is Eta Carina, which is a LBV, luminous blue variable, and this star underwent eruptive mass loss in the 19th century, where it lost about 10 solar masses in a very short space of time, in the space of a decade or so. And then WC stars, quite a few of them are visible as these sort of spirals, because the ones that are in binary systems and undergo a sort of colliding wind process. And because of the carbon content in these stellar winds, they form dust very quickly. So you can trace these spirals. So this is a dust spiral around a WC star in a binary system. So these Wolf-Rayet stars, the ones that are descendants of all stars, produce feedback throughout their lives. When they're old stars, they produce ionizing radiation in stellar winds. And when they're Wolf-Rayet stars, they also produce ionizing radiation and even stronger stellar winds. And they end their lives as cold collapse supernovae. They can produce dust both in ejector nebulae and if they turn into WC stars. And these are the stars that are going to be progenitors of stellar mass black holes that are 5 to 10 solar masses. They're also the progenitors of high mass X-ray binaries, and if they're in a binary system with a massive star, it could form binary black holes. And they're used as indicators of star formation in distant galaxies because they have a very characteristic spectral signal and they're very bright, so they can be picked up quite easily in external galaxies. So if we go back to the topic of the runaway stars in the galaxy, runaways can be determined or can be defined by their Z height. If their Z height is larger than some criterion, then we can say that they're runaways. In the past, the criteria that have been used are that they're more than 300 parsecs from the plane. And the idea behind this was that, as we're going to see, peculiar velocities of about 30 kilometers a second could also be taken as a criterion. So 30 kilometers a second for 10 megayears takes us to 300 parsecs. That's if the velocity was straight up. So that was the thinking behind that criterion. And a more recent idea is 3 times the H2 region scale height. Right, so that would be 160 parsecs. So now whichever of these criteria, Wolf-Rayet 124 is a runaway just based on its position in the galaxy. Peculiar velocity has also been used to determine whether a star can be classed as a runaway or not. And this very much depends on peculiar velocity with respect to what. So if you're looking at a cluster or a star association, it's quite easy to determine if some stars have peculiar motions with respect to the mean motion of the cluster. So this is in the IRyA-UNAM. So the red arrow indicates the sort of mean motion. The black arrows indicate stars that have sort of non-peculiar motions with respect to the mean, whereas the green ones have been determined to have peculiar motions according to some criteria. And the actual velocity that we take to indicate that a star has a substantial peculiar velocity has sort of evolved with time. And the classical work by Blau, which considered 3D velocities, that means the tangential plus the line of sight velocity, he put the threshold peculiar velocity at 40 kilometers a second. But the caveat with the Blau work is that you have to be able to associate a star with a cluster. So these stars could come from a certain cluster or group. And so 40 kilometers a second is the threshold there. Irene Cruz-Gonzalez put the threshold peculiar velocity, radial velocity, at 30 kilometers a second. This is line of sight velocity. And the idea behind this is that a typical velocity dispersion in a Hobby association is 10 kilometers a second, so this is 3 times that. And Moffat multiplied this by √2 because the argument was that if you only have tangential velocities, you've got 2 components. So 42 is the threshold velocity there. Tetzlaff used Hipparchus observations and looked at the distribution of velocities and separated it into 2 Gaussians. One Gaussian was the sort of the field stars, and the other Gaussian corresponded to faster stars. And the 2 crossed over about 25 kilometers a second. Kovalnicki took this 25 kilometers a second as being the threshold runaway velocity in the study of bow shocks associated with O B stars. And then more recently, in large-scale studies of Gaia data, Carretero Castillo used sort of the field stars, Gaussian fits to the field stars, and then compared essentially the proper motions of 2D velocities to the field star velocities. So there wasn't actually a threshold for here. And some runaways could have peculiar velocities as low as 16 or 10 kilometers a second. The main thing is that they're peculiar velocities with respect to what they're moving or through. So the question with these Wolf-Rayet stars that I'm going to be showing is where are they in the galaxy? You need to know where they are, and whether they're at high Z heights or in the plane, and how fast are they traveling. Because the Z height criterion basically tells you where the stars that have already run away, the runaway stars, are, but it doesn't tell you about stars that have only recently started out their travels. So when I started this project, I had thought about just looking at my favourite Wolf-Rayet stars and finding out whether they were runaways or not. And this could have been quite a sort of fruitful process, one publication per object, but it's not very useful from an astrophysical point of view. It doesn't tell you very much. And so instead, I went to the Wolf-Rayet catalogue, which is maintained by Paul Roller in Sheffield. This currently has 705 Wolf-Rayet stars, and 440 of these have Gaia source images. So I downloaded all the data for these stars, and after various processes and filters, I ended up with about 230 useful stars. And this process consisted of finding the parallax 0 point for each object. And in Gaia data release 2, the 0 point was a fixed value, it was 0.029 milliarc seconds. But for Gaia data release 3, it's dependent on the color and the position and the magnitude of the star. So it's different for different pointing or line of sight or positions of the stars, and it's different for different spectral types of star. And so there are fits for the 0 point based on these quantities. But as well, Jesus Mice had a correction to the fit by Indegren, the Gaia people, because bright hot stars need an additional correction to all the coefficients for these fits. So the range of 0 point corrections you get goes between 0.06 and minus 0.00 something. So there's quite a wide range of 0 point corrections. And that makes quite a big difference to stars that are more than a couple of kiloparsecs. And then there are data quality filters. There's the usual renormalization unit weight error, where the value that we hope to take is that the value is less than 1.4 indicated data quality is good. And in addition, I'm using parallax signal to noise ratio greater than 5. So using these filters, and after correcting the 0 point, I reduced the original 440 down to 230 useful objects. So although there are published distances to all of these stars, I wanted also to have self-consistent tangential velocities. And so you can construct a prior that takes into account the correlations between parallax and proper motions, and uses the covariance matrix. So the prior that is used in this Bayesian approach for calculating the distance is this theta is where we assume that it's separable in distance, speed, and angle. So the distance prior, the PR, is an exponential with scale length, and that scale length depends on position in the galaxy. So originally there was a sort of initial model of the distribution of stars in the galaxy, but since then it's been applied with actual Gaia results. So the scale length varies with the position. The velocity prior is a beta function, and the angle prior is just a uniform distribution. So the sort of results you get for the posterior are possible distances either in parsecs. And we want to take the median, and then we've got the uncertainties. This is the 5.95%. Take the 16.84%. And this is the speed. And they look similar, but they're shapes, but they're not exactly the same. And so this, so rather than taking a sort of a Gaussian or normal distribution for the error in the proper motions, we use one that takes into account the correlations between the parallax and the proper motion measurements. So then I take 1,000 samples of the posterior, and each sample is a triplet of distance, speed. So as well as the proper motions, in order to determine the complete movement of stars in the galaxy, you need the line of sight velocity. Now, unfortunately, because Wolf-Rayet stars are very bright and with broad emission lines, because of their wings, you can't, through normal spectroscopy, get the radial velocity from the Doppler shift of the absorption line, or the atmospheric absorption lines. There are some published values in the literature, but they're just from somewhere in the wind. So instead, have to use indirect methods. So stars that are binaries, if they've got published orbital elements, then you can take the systemic velocity of the binary as being a representative of the line of sight velocity of the star. And so 29 systems are spectroscopic binaries with published orbital parameters. If the stars are associated with ejector nebulae, then you can use the systemic velocity of the center of expansion, which would be representative of the center of mass motion of these systems. So only 3 systems qualify under that scenario. So for all the rest, I assume that the line of sight velocity is the component of the galactic co-rotation velocity at the galactocentric radius of a particular star. So this is the sort of geometry we're thinking about. We've got the sun, the galactic center, the sun's circular motion, and if we have a star here, then it's traveling around on its circular orbit. And we need to decompose this movement along the line of sight. So it's multiple applications of the cosine. And then we've also got the third direction that's perpendicular to the screen. So in the vast majority of cases, the line of sight velocity is taken to be the component, the line of sight component of the co-rotation velocity of the star. So with all that, we can calculate the Z heights above the midplane and express that in terms of the scale height of the OB stars. So here I divide all the Wolf-Rayet stars by spectral type and subtype. The late WN stars are here, the early WN stars are here. These are all the B stars. This parameter eta is their Z height divided by the scale height at the position of the star in the galaxy. So we can see that the WN8 stars have many objects that are above 1 scale height of the galactic plane, whereas other spectral types have do not get as high above the plane. You might think that if the WC types are the sort of more evolved stars, then they would have got higher if they come from a similar population. But there's nothing to say that there's a trend across this diagram. And these are the O1F WNs. These are the very massive stars, 60 plus solar masses. So all of these are reasonably low scale, as you might expect, because those are the ones that live messed up. So even from this sort of first exploration, the WN8 stars seem to be different to the others. And there are also an awful lot of stars in the WC9 class. The half-filled symbols are the ones that are in this WNC transition class. And so they appear both here and in the appropriate places and these other diagrams. The colours don't have any meaning at all. And the error bars are due to the uncertainties on the distances. So we can do the same for peculiar velocities. Here are marked 30 kilometers a second, and the labeled stars are the ones whose peculiar velocities are above 60 kilometers a second. And again, we see that this WN8 spectral class has 4 stars in it with peculiar velocities above 60. And we're going to see shortly that 60 is quite an important speed. You can't really say that there are any trends. So with the velocities, with the positions, the proper motions, the distance and the line of sight velocities, and the Galpi stellar dynamics package, we can integrate the trajectories of all these Wolf-Rayet stars, the runaway ones, backwards in time. So use the Milky Way potential 2014, which is the one that's recommended by Bowie, who wrote Galpi, as being the most representative, the best approximation to the galactic potential. And it consists of a bulgy disk and a halo component. This is the contours of the potential, and these are contours of the density. And once again, I remind you that using the parameters for the solar position and the velocity, circular velocity of the sun's position, divided by U. So if you remember back to the beginning, these coloured bands are the represent the spiral arms. The red stars indicate current position of the star. Black crosses 5 million years ago, open circles 10 million years ago. So these are the WNL stars and the very massive stars, which are this O1F and WN class. We can see that most of these follow the circular motion. The different colours here, the magenta are the stars that have peculiar velocities above 60 kilometers a second. And the greeny colours are ones whose peculiar velocity is below 30 kilometers a second, but their Z height qualifies them as a Wolf-Rayet star. So of the total sample of 90 of these spectral types, 36 are runaways because of their peculiar velocity, and 16 are runaways because of their height, and there are some that are both. And we can see that there are concentrations of these stars very near to the star-forming regions. This is the Carina arm. So we have the Carina OB1 region, Westerland 2, and NGC 3603. And this region here is along the line side to Westerland 1. Cygnus region is around here. There are fewer WNE early type stars in the sample. 17 of the 47 are runaways because of their peculiar velocity, and 14 because of their Z height. Again, there is some of both. And we don't see any particular concentrations here, apart from around here. This is a different club than the Westerland 1 group. And this would correspond to the roughly towards the NGC 3603, but there's nothing closer than the green arm. So the distribution of the WNE stars, runaways, is different to the WNL stars. And then there are more WC stars. We can see that these are much more spread out. They're not clumped together like the WNL stars were. Again, 36 are runaways because of their peculiar velocity, 30 because of their Z height, and the sample is a bit larger. And these are more widely distributed. So this sort of goes along with the idea that these stars are sort of later stages in the evolution of these associations of massive stars that are dispersed in galaxies. We can look at the same thing from the side. And again, this is the center of the galaxy. This is galactocentric radius for stars whose phi value, which is 180 minus galactic longitude. So this is, if the sun's up galactic centers here, these are the stars on the right, and these would be the stars on the left, over here. So the WNL stars, we see that they're grouped in these clusters along the Carina arm mainly here, and then we've got some points that correspond to Cygnus. And it's tempting to think that these stars had a common origin, that we can trace them back to the same volume at some point in time. But if you look at it closely, then it doesn't really work out that way. I've got no idea of knowing what the time is. That works, does it? Okay. Can I see that file? So we can use the idea of kinetic age for stars that have high peculiar vertical velocity and negligible peculiar velocity in the other directions. We can say that, well, they were launched from the galactic midplane. And so for those stars that the only peculiar motion really is in the vertical distance, several of them can be traced back to the midplane about 6 million years ago, which is sort of can be reconciled with the evolution times. I've got a lot to say about the WN stars. Whereas the WC stars, these ones, some of them have very interesting trajectories. They appear to start higher and even now are quite high above the galactic plane. So this could be because they turned around and coming back down, or it could be because they were from some event that occurred at a high altitude and they're coming back down. And so the ones that again have a substantial vertical component on the spin, the kinetic ages to get back to the midplane is only 4 million years, which is a bit counterintuitive if the WNLs, which you would think were younger stars, take 6 million years to get back. So there are two scenarios that have been proposed for producing runaways. Two main ones. One is the dynamical ejection scenario, which we've seen quite a bit of in different contexts. This was originally proposed by IRyA-UNAM in 1967. And the idea is that in the process of star formation, multiple interactions occur and some stars are ejected with high velocities. And the well-known example of this is in the Orion molecular cloud, where in the BN region there's radio frequencies as evidence of all these fingers and bullets of gas that's being expelled by some highly energetic process. And the yellow arrows here indicate the proper motions of massive stars that have been presumably ejected into something. Although massive stars in this context seems to mean up to 15 solar masses, 7 solar masses. So these are not my massive stars. They're not really massive stars. And it took a while before other similar regions were found, but there's this one close to the line of sight of the galactic center that Zapata studied 5 or 6 years ago. So there are energetic phenomena that occur in star-forming regions that could be responsible for ejecting these massive stars early on in their lifetimes. If they originated 6 million years ago in the disk, in the star-forming region, then it was something in the star formation process that sent them careening off. So the idea is that it's multiple interactions with binary systems. And so the sort of interactions that are anticipated at flybys or exchanges. And both of these sorts of interactions can increase the negative potential energy of the binary. And so the star that encounters or is ejected leaves with a higher kinetic energy. And so this has been studied in many contexts, and also N-body simulations have been performed of numbers of stars with either all the same mass or an INF. And it's found that multiple interactions with multiple binaries can form runaways with different velocities and different probabilities and frequencies. So this little insect is the linear scale of this main graph. So in this insect, all of these massive star lines around here. So most of the interactions lead to massive stars that have velocities of about 20 kilometers a second. And a much smaller fraction will achieve higher velocities, like 60 or 100 kilometers a second. But you can produce them through this process of multiple interactions with multiple lines. And the very massive stars, the ones that are about above 60 solar masses, can be formed through collisions. If the binary is forced closer and closer, it can eventually merge. And those, even those very massive stars can be ejected through the same processes. One result of this work by Peretz is that if it's a binary that's ejected, then the maximum velocity that an ejected binary can have is about 150 kilometers a second. And one of the objects in our sample, Wolf-Rayet 148, is a runaway binary, massive binary, and it has a velocity well above 100, but less than 150 kilometers a second. And the other scenario that's been proposed is the binary supernova scenario. So in this scenario, you have two massive stars in a binary system. The more massive one evolves first and goes supernova, and the other one goes flying off. And so numerical simulations, including mass transfer and mass loss, have been done on many systems. And it's found that 22% of these systems merge before the first core collapse. And then of the rest, 86% lead to disrupted systems, will be ejected stars, and 14% are left with systems that are still bound after the supernova. So it's found that most of the ejected secondary stars, those are the ones that are still massive stars after the supernova, are what's called walkaways. They have velocities less than 30 kilometers a second. And almost no ejected secondaries have velocities above 60 kilometers a second. So it seems that in order to achieve the highest velocities, above 60 kilometers a second, it has to have been the dynamical ejection scenario, the previous one. The one from the multiple interactions of multiple lines during the star formation process. So a few final comments. If massive stars run away, then they're going to change the effect of the feedback they have on the interstellar medium, because they're going to leave their original molecular cloud and spread their joy throughout the galaxy. So feedback is going to occur in different places, not just in the molecular cloud where they formed. And of the stars that I've studied, at least 22% of them, of all the Wolf-Rayet stars, are found to be runaways. It looks like a higher fraction because it is a higher fraction of my sample, but my sample is not all Wolf-Rayet stars. And going back to binaries, binary stars can change the time scales for the evolution of these massive stars and the outcomes. For example, some of these Wolf-Rayet WN8H stars, it's thought that they're actually binary stars where either there's been a merger or a common envelope event that's ejected the envelope. So they could have much longer lifetimes than a single star scenario suggests. And the WN8 subtype is strange compared to its subtypes either side, particularly the WN7 subtype. So it doesn't look like the WN8 stars evolve into WN7 stars because they have a completely different distribution of runaway stars. And they're for you to contemplate. Take some questions. Thank you.
So Jane.
I have some very simple simulations of just clouds dropping into galactic disks. And on the other side, you have a disk here and the cloud drops, and there is a big block of gas falling into the other side of the galaxy. These are very simple. I don't know how realistic they are, but I imagine that something like that, like a dwarf galaxy or a large high velocity cloud, might generate a star formation event that with a lot of velocity, vertical velocity. So do you see in the Gaia data associate velocity associations in non-Wolf-Rayet stars associated with this?
No, because I haven't looked. I'm not. There are many studies of old stars. There's about 4 in the last year or so on runaway old stars and the dynamics of old stars. And most of the conclusions are that the associations where they form just dissipate on a time scale of about 8 million years. So my original intention with the this study was to try and trace the runaway stars back to a particular star forming region. But it doesn't work like that because the star forming region has gone. So the clouds falling in, people will have studied that, not me.
So you're favoring this interpretation that these interactions happen during the formation process?
For the WNL stars in particular, they seem to be closely associated with the star forming regions, and it's in particular the WN8 subtype has high velocity. If they have peculiar velocities above 60 kilometers a second, then they didn't form from the disintegration of a binary system when one of the stars went supernova. So in order to get higher peculiar velocities, then they needed to have been in a dense stellar environment at some point in their life.
So that's my question or comment. So then, as you mentioned, these systems, because they are very massive, the stars are very massive, they will not form in Orion type systems, but they will form actually in clusters that are much more massive. And if this happens at the formation stage, these clusters have larger amounts of stars and they are very gas rich. So say you can have already a population of 10 to the 4 solar mass of stars and 10 times more gas in a few parsecs or in less than 10 parsecs. So presumably they will have to skate a significantly larger potential well. So then this velocity, this threshold velocity that we are defining of say 30 kilometers per second probably needs to be even higher.
It doesn't seem to need to be. There have been a lot of studies by people like Janet Drew and even Charlie Roman on regions like NGC 36 or 3. And there are some very massive stars that are clearly sort of at the edge of this region, heading away, and that can be traced back to the central point. And the velocities are not much more than 30 odd in those places, and they are less than the 60 odd, but they are heading away and expanding. So
it may have been higher velocity when they were ejected, but once they get out of the potential well, they've lost.
So now you see them at 50 kilometers per second, but probably they needed like 100.
Together.
maybe.
Right.
And there are many of these very massive star-formed regions along the Korean front. They've got stars shooting.
Carina is very big. It's it's not like really concentrated, but okay.
Yeah, whereas the Korean arm, which has got like tens of star-formed regions along the line of sight, it's very difficult to disentangle.
Okay, we have.
And would it be possible that, for example, in order to test the supernova ejection scenario, to see if the supernova events that happen in the Milky Way And then since you have calculated the trajectories of the Wolf-Rayet runaways, so maybe there could be a chance that some of these supernova records could at least point toward some runaways, and maybe could see like okay, this runaway could happen because of this supernova. Could it be possible to do that?
Well, supernovae are very sort of diffuse events that aren't visible for that long, 20,000 years, and then it's going to merge with the background and with the big extended things. And also we don't know the distances because it's gas. So, yeah, I mean, with radio observations, you can detect supernova remnants further away, but the optical finest ones, they might move on.
Yeah, but also for conservation of momentum, the other star will be ejected.
Yeah, the companion star would have gone. And so, I mean, there are pulsars with high velocity, but that's a sort of kick from the explosion process. So, I mean, do you look for the supernova event? Do you look for a pulsar that's shot off in one direction, or a black hole? You're not going to see that.
But in those cases, they are associated, they're not very far from the supernova, and you can see the bow show.
Yeah.
Hearing through this.
Yeah, I mean, bow shocks is a good way of comparing. So several of the sample that I've got, I need to do the cross correlation with the bow shock databases to see if any of them are in there. And there are quite a few objects that I think you could get better line of sight velocities because they're associated with ejector nebulae that haven't had their expansions measured. Not a huge number. So yeah, line of sight velocities is a big problem with hot stars. Jesus Mice has got a project on all stars trying to get better radio velocities for all stars, but that's still not the Wolf-Rayet.
In your diagrams where you have the galactic coordinates with stars, I saw that you have like a more dense sample on the left side of the diagram compared to the right side.
Mm-hmm.
Is that a statistical like bias because you have a very limited sample, or is it like something that it is like real?
Well, it's because of the Carina line of sight. Most of those objects are on the Carina line of sight.
Oh.
Which is that side of the galaxy. And I think there's a lot of star formation on there because of the bar.
Okay, so it is like correlated with the star formation rate on that side of the galaxy.
Yeah. Yes, the Cygnus region was a big disappointment. I thought there'd be more runaways associated with Cygnus, but there are about 4 or 5. And also, what we knew about the Cygnus OB regions, it seems is not really true. It's a lot of several smaller clusters, all of which are moving away from sort of central events that occurred at 8 minutes ago.
Question for Jane? We have no questions, so
well, you showed us like the pictures with the Wolf-Rayet nebulae and subtle star, but in a lot of those cases, we do not see like a clear bow shock, even if we know they are runaway stars. But I was wondering if that happens because we are of the line of sight that we are getting from the object.
Well, it could also be the velocity. I mean, or the where they are in the galaxy. Yeah, like this star isn't in the center of the bubble, but on the other hand, this isn't moving particularly fast.
Yeah,
this is going 30 miles a second. This one isn't a sphere; it's like a donut.
Mm-hmm.
And
M167.
M167. The people say there's a bow shock in that direction, but I don't think there's any strong evidence. And also, where it is in the galaxy at 330 parsecs, the gas is not very dense.
Yeah, no, the 3D structure of this bubble is actually like a bubble. Okay, the star is a little bit further away from us.
Yeah.
Can I ask a question? have you looked at any Wolf-Rayet stars that are still in clusters? Or are these all isolated?
I looked at all the Wolf-Rayet stars in the catalogue.
Okay.
Right, there are 700, well, there were 710, and there are only 705 now. And I've got to write to Paul to tell him that two of them are cataclysmic variables.
Are any of them still in massive clusters?
Yes, but as I said, 440 have Gaia DR3. So there's like 250 that don't. And most of that is because a lot of the new Wolf-Rayet stars are not identified by their optical spectra, but by infrared criteria. So a lot of these are sort of still embedded in clusters. And those are the ones that probably don't have Gaia DR3.
I wonder if you could catch them early runaways by looking at those.
Well, you could if they were seen, but most of the ones that I've got are like the sort of the traditional ones that have been in the catalogue for a long time.
So if we don't have any further questions, we thank Jane. Don't know if they will be after Coloquio.
Yes, I'm not sure.